So, hi, welcome to lecture 24 on resolvents and non-expansive operators. So we're going to continue the analysis of monotone operators here. So remember that now all these operators we consider are set valued in general, so multi-valued operators, and also we call these identification of operator and its graph. Okay, and of course you also need this important notion of monotonicity, which is that this inner product of image difference of things in the image and difference in the pre-images, this inner product has to be non-negative. Okay, so lecture today is resolvents and non-expansive operators. And expansive is written with an A, so it's not costly, but it's not expanding. And the resolvents will become clear later. I think this is true for today. Let's take this one. So before we come to these notions of the resolvent and the non-expansiveness, let's collect a few more things which we need to know about monotone operators. So first is proposition 24.1. It's just probably just a simple observation is, but for every monotone A, which maps our X multivalually to X, there exists a maximally monotone extension. Exists maximal monotone extension A bar, again multivalued. And extension means that the graph of A is actually a subset of the graph of A bar. So kind of every monotone operator can be closed to a maximally monotone one. So not closed in the topological sense, but we can make every monotone operator maximal. And the proof is actually it's a non-constructive general proof. If you define the set, so like this is script A as all the operators, the multivalued ones from X multivalued to X, this is then there's a typo in the script. It has to be only monotone operators. So these are all the monotone operators on A from X to X, which contain the graph of A. This set here is partially ordered by inclusion. And then again we can do that again. So now we can use the Zorn's lemma, which says if you have a partial ordered set, then every chain contains a maximal element. Zorn's lemma, which is a general lemma in set theory, says there is maximal ordered subset and A0 subset of A, and then we define this A bar as just the unions of all the A stars in this maximally ordered subset, and then that's it. This is and this means union of the graphs, right? We identify the operators and the graphs, so we take the graphs, unite them, and then consider what comes out of this. And because they are this is an ordered subset, which means these elements in A0 just get larger and larger, so it's actually really a union of increasing graphs. And so if you unite all the things together, you get something which is maximal monotone by construction. So that's a straightforward existence result, which doesn't tell us how many of these things exist and how they look like. But anyway, they exist. You can extend every monotone operator to a maximum monotone one. Okay, now let's come next proposition. It's also a result which is pretty helpful in the following. If a multi-valued map, actually it's only a single-valued map now. So you have a single-valued map which is continuous and monotone, then A is maximal monotone. So continuity plus monotonicity implies maximal monotonicity. Of course, most monotone operators are far from being continuous because they may be multi-valued and have some of these closed jumps and stuff. But anyway, so some of them are continuous, and if they're continuous, they also have to be maximal. Okay. Okay, so this works like this. Assume for some tuple x star x prime v prime. Oops. So that's the typo. X prime v prime in sorry, I messed that up. So it's just for some x prime v prime, I guess. We have that the inner product of v prime minus ax and x prime minus x is always non-negative for all x. So assume that, and our aim is then to show that v is an a of x. V prime is an a of x prime. So for some tuple ax x prime v prime, we have the inequality for all x, and our aim is to show that this, because if this implication always holds, if this implies that this is the case, then this a is actually maximum monotone. So what we do is we take this holds for all x, and we take a special one. We take x prime plus epsilon times u for some epsilon non-negative, positive, and u in x. Then we have a look at what this guy here is. Then in this case, then this will get that's v prime minus a of x prime plus epsilon u, and here we get x prime minus x is then just x prime minus x. So actually, maybe it's simpler to use minus u epsilon u. It also works as well. Then we get here epsilon u, but we can get the epsilon out and divide by it. So we end up with this. But now this guy here, because of continuity, if we now let epsilon go to 0, this ends up at a x prime. So what we get is that we have v prime minus ax prime times u is positive for all u, especially also for minus u, because we have used minus plus epsilon over here anyway, and this implies that v prime minus ax equals 0, which is what we wanted to show. So actually I don't want to show it in, but we can show even equality because it's single valued. So continuous plus monotone gives maximally monotone. Okay, so that was these preparations. Good things are just good to know about monotone operators. So now just recall that we've already seen that now the prox of f was the same as identity plus subgradient of f to the minus 1. And you've seen that this is actually always single valued here. This is even though this subgradient is multi-valued, adding identity is still multi-valued, but after taking the inverse it's single valued. So this motivates that we can do the same, consider the same constructions for monotone operators. Identity plus A and then take the inverse. And this gets a special name. That's the following definition. So if you have a multi-valued operator from x to x, and so a multi-valued nonlinear, and then this operator identity plus a to the minus 1, which always exists in the sense of multi-valued operators, we denote this by JA. This is called the resolvent. Okay, that's already the definition. And there were more notions of resolvents in other fields. For example, for linear operators, there's also they look more or less the same. Sometimes with a minus, not with a plus. And you may also see that it looks like it's a little bit related to eigenvalues, right? If you take your lambda I plus a, then if the lambda I plus a has a kernel for linear operators, then lambda has an eigenvalue. So this is the eigenvalues are exactly the places where this inverse would not exist. Okay, but here it's with a plus, and there's no lambda. Of course, we could introduce a lambda in front of a, but we don't right now. And more importantly, this a is non-linear, so the eigenvalues that just do not exist in this case. So, and then with this notation, we could write that the prox of f is the resolvent of the subgradient of f. Okay, so the prox is always single-valued. So we can ask, what about the resolvent of a general monotone operator? And turns out the same is true. Proposition 24.4. We have again a multi-valued from x to x. The domain of a is not empty, and then this JA is at most single valued. Okay, so maybe empty, but it's at most single valued. Okay, let's prove that. And we have got monotone. So you could define the resolvent for any multi-valued operator. I just noticed that in the lecture notes I've written monotone. Of course, you don't need that. You can define that for all operators if you like. But this single valuedness, you need monotonicity. Okay, so to show that it's the most single valued, so we assume that we have xi. It's both in the image of the resolvent for two different x1 and x2, both in the resolvent, and then let's see what we can get out of this. So then this is equivalent to say that y, so we'll just bring the inverse to the other side, y is in the in identity plus a of xi, which is of course the same, so this here is xi plus axi. Bringing xi to the other side, it's the same as saying that x minus xi is in axi. So, okay, and now we write down monotonicity. So monotonicity is, now we have two, we can have these things here for I equals 1, 2, here as well. So we can write down, we know that 0 is smaller than the inner product of these images with the pre-images. So the inner product of the images are y minus x1 minus y minus x2 times x minus x1, x1 minus x2. So, but if you look what this is, so the y cancelled, and this in front here is minus x plus x2, which is the negative of this, so that gives you minus x1 minus x2 squared, and this implies that x1 is equal to x2. So funny enough, just as monotonicity implies that resolvents are only single valued. Okay, well there's more. Resolvents are even better. So they are not only single valued, which I find pretty nice. They are also non-expansive. So, but first, let's define that. Definition 24.5. So now a single valued map T from x to x is non-expansive with an A, not with an E. If we have that the distance of images is not larger than the distance of pre-images. Okay. So in this, you notice this is the same as saying T is Lipschitz continuous with constant 1. There's non-expansive, and we also have T is a contraction. And sometimes people also call this contraction, but I don't think it's really a contraction because distances can stay the same, right? The identity is fulfills this, but I would not say that the identity is contracting anything. A contraction means that the difference of the images smaller than q times the distance of the pre-images for some q smaller than 1. Okay, this is something you already know from Banach's fixed point theorem, that if you have a contraction, then iteration there will just converge. And we apply the same things to multivalued operators for a second. So of course we can just use the same definition, but then we have to choose elements in the images. But we'll only need this for a very short time here. Because you will see in the end that multivalued operator that is non-expansive is actually single valued. Okay, so now comes now we're going to prove. We start with the preparations for the proof of Minty's theorem. Okay, and the important thing is that these resolvents have a kind of interesting relations with non-expansive operators, and no, not the resolvents. Monotone operators have an interesting relation with non-expansive operators in two ways. One is via the resolvent, and the other is via Minty parametrization. So here is a proposition. It's called Minty parametrization. Okay. So we work on Rn and we define a map J on Rn times Rn into itself, a linear one. And it should look like J of x and v is, here we take x plus v, and here we take minus x plus v. So in block matrix notation, this is, we take x and v, and then here we have identity, identity, minus identity, identity. And I think in the lecture notes I wrote 1, but I think you know what I mean. This is a linear map, and it has an inverse, and the inverse looks like, you probably can guess what the inverse is. I probably made another typo there. I think I made a typo. So because you probably know what this is, right? Here, this is if you take n equals 1, then these are all 1 by 1 matrices. So the matrix is actually 1, 1, minus 1, 1. And you probably remember that this is a rotation which rotates the r times r, the r2 plane, 45 degrees to the right. But it also expands by a factor of square root of 2. So if I multiply this by 1 over square root of 2, that's actually really a rotation. So then we know what the inverse is. The inverse is rotating to the left and shrinking again. And I think we need to do it like this, 1 over 2. And then it's rotating to the left would be identity minus identity here, identity there, identity there. Z times W, which is 1 over 2. And then here we have Z minus W, and here we have Z plus W. Okay. Oops. And now this is just this map we're going to use. And now the comes the statement. So assume that two set-valued operators A and B from Rn to Rn, actually I should have written x here, but anyway, they are related by the following thing, that the graph of B is actually the rotation of by 45 degrees to the right of the graph of A, and of course then the graph of A is then the other rotation, and I omit the scaling, which is here just for simplicity. Of course the scaling is involved, so this B is actually rotated and scaled, and this other one is also rotated and scaled. So maybe I try to draw a picture, but I hope that works. So this is the plane where I want to draw the graph of A, and let's try something maybe like this, and then like this, and probably like this, and like this. So this could be the graph of A. So now what does it look like if I rotate it by 45 degrees to the right? So now it's a bit tricky here to obtain. So of course maybe I could help myself if I would return the axis here at 45 degrees. Then, so these are the new axes somehow, and then I should be able to make a copy here of how B looks like. Right here, this goes slightly up. Here it's almost flat, and then we have something like this. Right, so this red graph here is the blue graph corresponding to this red coordinate system. So this A here is monotone. This is how I drew it. So it can go up vertically, and it can go to the right horizontally. But after rotation, these very steep parts here, they have no slope 1, and the flattest parts have slope -1. So and then this is actually what is true. Then it holds. I think we have two things. This A is monotone if and only if B is non-expansive. This is what the picture says, tells us, and it's actually true. And second, we can even relate B and A by formula, and this is a little bit weird. So this B is what you get if you take identity minus 2 times identity composed with the resolvent of A, and also A you can get it by I minus B to the -1, then post-composed with 2 times identity minus the identity. Okay, so this is how the relation between this function A and this function B over here. Okay, let's prove it. Okay, and what we do is, so let's consider images here, Zj, Wj in, not in, but equal to J of, capital J of xj and vj. And this means this is here xj plus vj, and this is minus xj plus vj. Okay, and now what we consider is, and we consider the difference here, z1 also for I, j equals 1 and 2. So now we consider z1 minus z2 squared minus w1 minus w2 squared. And the first thing to observe is, so if we have a close look, we can rewrite this guy here as, and this is now a little longer, it's z2 minus z1 minus w2 minus w1, inner product, so it's plus, and here inner product z2 minus z1 minus w2 minus w1. If you expand everything and do the arithmetic, then you see that these two things are actually the same. So now it's not that hard to identify these, express these things here as x's. So for example, here we can do it as z2 plus w2 plus z1 plus w1. No, sorry, it's minus actually. Minus. And here we have z2 minus w1 minus z1 minus z2 minus w2 minus d1 minus w1. So this is just rearranging things here. And actually, by the inverse here, one sees that this here is 2 times v2 minus 2 times v1, and here we get 2 times x2 minus 2 times x1. And then we see this is here is 4 times v2 minus v1, x2 minus x1. So if we look at this, it's all equal, it's all equations. So what we can see is, we can conclude that we have that z, let's see, so let's do w1 minus w2 squared is, or not without square maybe, it's smaller than z1 minus z2 if and only if this inner product here, v2 minus v1 times x2 minus x1 is non-negative. And that's already it, right? That proves the first point. So this v and, if this v and zw and xv are connected by the j, then we see that this inequality is equivalent to that inequality, and this here says that so if these a and b are in relation by applying the j, then this says that b is non-expansive, and this says that a is monotone. So you see these two things are related by if and only if. So that was the proof of the first part already. Okay. Let's come to the second part, where we have these funny equations which relate these two graphs. So for the second part, so let's just once write out what this means, that the graph of B is equal to J of graph of A. It means that if the W is in J times the graph of A, so it means that if we have that for some v which is in AX, then we have that z is v plus x and w is equal v minus x. So this is what this relation here shows. So if we have something in the turned graph, so in graph of B, then this z and w should be of the form v plus x and v minus x for some v in A of x. So, but then this is actually equivalent to saying that z is in identity plus A of x, and v is equal to z minus x, and z minus x minus x, which is actually z minus 2x. Okay, so right here, this v is in A of x, so this first thing gives us this, and we can say also that v is z minus x. This goes here, so plug it here. W is z minus 2x. So hence we can say we have w is in B of z if and only if w is equal to z minus 2x for some x in identity plus A to the minus 1 of z. So from here, so that's what we learned up here. And this is basically already all what we have, right? Yeah, if we plug this here, so this, then we have that, right? So so w is then in z minus 2 times this, 2 times identity plus A to the minus 1 z, and that's if we look here, exactly what we wanted to show. So w is in B of z if it's in here, so this has to be these two things are the same. Okay, this is for the first thing, and for the second, if we now have if we have B is equal to identity minus 2 times identity post-compose with A plus A to the minus 1. So we, of course, can bring the identity to the left-hand side, B minus identity. Oops. Sorry, there's another typo. So we bring identity to the right-hand side and swap the sign so that we get identity minus B is equal to 2 times identity post-compose 1 plus A to the minus 1. Then we compose from we compose from the right by A plus identity, and from the left by identity minus B to the minus 1. So we get I plus identity is equal to I minus B to the minus 1 for 2I, and then we just bring the I to the other side. So it's A is equal to identity minus B to the minus 1 post-compose to identity minus identity, and this is what we wanted to show. So it's just solving an equation, so there's nothing deeper behind that. Okay. So that's actually nice. It's not really that it's really needed, but this shows us that these things are kind of in correspondence. And this already shows us that this is out of an monotone operator. That's a way to construct a non-expansive operator out of it, right? If we have a monotone operator and we can form the resolvent, then this expression here is then non-expansive actually. Okay, so and maybe I before the break I'm gonna prove Minty's theorem here, and then we're gonna make the break and try to make the rest of the lecture. So Minty's theorem. You already seen the converse of Minty's theorem, saying that that if identity plus A is onto for maximal for monotone operator, then A is maximal monotone. Here we're going to prove the converse. So if A is maximally monotone, then identity, now I use a non-negative number here, lambda A, I plus lambda A is onto for every lambda non-negative. So that's the converse of what we had. So we know that if for monotone operator this guy here is onto, then A is maximal monotone. Here we get the implication in this direction. And another thing is, moreover, the resolvent identity plus lambda A to the minus 1 also maximally monotone. Okay. So the proof is actually not so complicated. I thought it was much more complicated. So first, without loss of generality, we assume lambda equals 1, right? This doesn't change anything, because if A is monotone, if and only if lambda A is monotone for positive lambda, for 1 or for any. Okay. So now we make the trick that we say that this A is maximally monotone if and only if the B from the previous proposition is non-expansive. And maximal with respect to graph inclusion. Right, this is the maximality stays the same, right? If you turn the graph, if it has been maximal within the class of monotone operators, then after that it's maximal within the class of non-expansive operators. So, so we just need to conclude, or now construct check that B then is maximal monotone if we have this condition here. Okay, so now we use another general result. So we use the following thing. And this goes like this. If we have, oh no, that's bad notation here. If we, let's say, have U is a subset of Rn, any subset, no restrictions whatsoever, can be anything. And you have a function f, which is defined on U into R, let's say M actually, Lipschitz continuous. Then there exists an extension f bar from Rn to Rm of f with the same Lipschitz constant. So at first I found that result pretty remarkable because there's just no assumptions on U whatsoever. It can be as complicated as a subset as you may, not measurable, whatever, any subset. And then from mere Lipschitzness, it should follow that we can extend it to all things. Why is that? Yeah, the reason is that Lipschitz continuity is kind of a long range property. Because it says if I have a special value here, it says something about the function value at every other place there can be. Because it's if I know my function value is, for example, 0 here, if I am at distance 1000 at this value, I can only have the value 1000 times the Lipschitz constant, nothing more. So it's a long range property. The value at one point restricts what the function can do at all other points. It's different from continuity or smoothness or whatever. Lipschitz continuity is a long range property. And then if you thought about this for a while, then it seems to, well, okay, at least on the real line, everything I'm fine now. So there has to be a Lipschitz extension. And if you think about higher dimensional space, it may find it a little bit harder to imagine, but for me it's not a surprise. The longer I think about it, the more natural it appears. So I'm not going to prove it here. The proof is technical and long, but so the construction is clear. It's basically the same as we did with the monotone operators. You just you consider the set of all Lipschitz continuous functions which extends this here to any larger set, and then you have to first show that this is not empty, and then you consider again by Zorn's lemma there exists a maximal element, and then the difficulty is to prove that this maximal element even actually has the full Rn as domain. That's the hard part to do here. That this Rn is then after it's then full. Okay, and we're not going to prove this here. What I wanted to say is this is called theorem 958 in the book Variational Analysis. By Rockefeller and Wetz. Okay. So that's again non-constructive result relying on Zorn's lemma. So then we get some. This shows us now if it's maximal graph inclusion, shows us that B is maximal non-expansive. If and only if the domain of B is the full Rn. Because if it wouldn't be, I could extend it even further. That's the catch. So that's what we learned from this green theorem here. So from here we can conclude now that B is non-expansive and maximal. It has to have full domain. There can't be any point where B, the image of B is empty, because if it would be, we could fill it up in a Lipschitz way. Okay. But this is the case, so this here, the domain of B is full Rn, if and only if the domain of identity plus a to the minus 1 is also Rn. This comes from our formula before. It has to be non-empty everywhere, because we had this formula that the B looks like this. And this has full domain, so this has to have full domain, so this has to have full domain. If this wouldn't have, then the full thing would not be a full domain. And that's already it. Yeah, this says if and only if I plus A is onto. Good. So, and finally, identity plus a to the minus 1 is now single valued, we know that from before, and continuous. Again, by this here, for example, you see that this is continuous, and this would not be continuous, then this B would not be continuous, and B is even Lipschitz. So, continuous, and hence it's a maximum monotone. Also from before. Okay, so that was Minty's theorem, and the magic in Minty's theorem is that or the magic why it works is if you turn the graph by 45 degrees to the right, then we are in the Lipschitz setting. In the Lipschitz setting, one can prove by a non-constructive argument that the function has to have full domain in case if it is maximal, and if the domain is not the full space, then we can do further Lipschitz continuous extension. Okay, short break, and I again could not manage to dig up more dead jokes. I think this account is exhausted, but anyway, maybe you forgot about the old one. So 2 minutes break for me and for you, and then we do the rest of the lecture. Okay, so now I'd like to show you also another graphical interpretation of the resolvent. So you can also, like we now did this graphical construction of this rotation of the graph, and also the resolvent comes kind of from a linear transformation of Rn times Rn. And to do so, we consider map M at index by lambda, which again maps Rn times Rn into Rn times Rn, and the map should act on x and v, like here we should get x plus lambda v, and here we should get x. Maybe I try to illustrate what this is doing. So if you have here the x and the v-axis, so the unit vector here, it's a blue one, and here we take a red one for v. So then if we now map them with m lambda, where do we arrive? This, I don't know, so maybe I hope I don't screw it up too much. I think yeah, so this unit vector x, so this m of 1 0, it gets mapped to the vector 1 1, and the vector 0 1 get maps to lambda 0. So actually the blue one here ends up there, and the red one ends up somewhere here, depending on where lambda is, but they are on the same level over there. So it's oh, sorry, that was wrong. The red one is ends up here, something like that. Okay, so it's not totally. So this is what the linear operator here does to the plane. It tilts them up like this and flips the other one around down there. And what is then true? So we have x is the resolvent of a applied to z. That's if and only if lambda a, let's say. If and only if z and x is in the graph of j lambda a, and this is nothing else but identity plus lambda a to the minus 1. And so this is if and only if I just here maybe first here, so z is actually equal to identity plus lambda a x, and yeah, so, and we can rearrange this to z minus x divided by lambda is in a of x, and writing it again as a graph, this means that x and this object z minus x over lambda is in the graph of a. But now since, so if we apply m lambda to this guy here, to x, z minus x divided by lambda, we get exactly z times x, zx. So and this shows us that the graph, oops, of j lambda a is actually m lambda applied to the graph of a. So that's also the resolvent can be constructed by kind of linearly deforming the graph. That's not of practical use as far as I see, because you kind of need to have this inversion somehow, but anyway, that's one way of seeing it. Okay, so resolvents have special and nice properties. It's not so simple to see everything right now from scratch, but you've already seen that resolvents are continuous from this here, and actually from this one can see something more. Okay, but we come to that. So, and the main thing which makes resolvents interesting is that they have kind of contraction properties. So not really contraction. So the first thing I want to prove is that resolvents are non-expansive. That's the first nice thing. And the second nice thing, they have a slightly better property. So they are, in general, they are not contractive. That's not true. But they are so-called firmly non-expansive. Okay, let me show you what this means, firmly non-expansive. So in firmly. So a map A, now single valued from x to x, is firmly non-expansive. If we have for all x and y that ax1 minus ax2, and it's maybe a nonlinear operator, squared plus identity minus ax1 minus identity minus ax2 squared, if that's smaller or equal to x1 minus x2. So that's firm non-expansiveness. So without this term in the middle here, that's the non-expansiveness inequality. Then you can remove the squares. So this is a little bit more. So not only this here is smaller than that, but even if I add this guy here, it's still smaller than that. Okay, and that's the kind of, so it looks a little bit weird and at first, so it's not simple to find a good geometric interpretation. I think there will be an exercise which lets you work out what this means for linear maps A, linear symmetric maps, and then you probably get a little bit of better understanding what this means here. Okay, so but the significance for us comes first from the fact that resolvents have this property. Almost. First term, so if you have a subset of X, non-empty, and an operator A which is defined on the subset, single valued, so then the following are equivalent. Then equivalent 5 things. First is A is firmly non-expansive. The second is identity minus A is firmly non-expansive. The third one is that 2A minus identity is just non-expansive, not firmly but still expansive, non-expansive. The fourth one is for all x and y and d, you have that ax minus ay squared is smaller equal x minus y times ax minus ay. And the fifth one is for all x and y in D, it holds that 0 is smaller equal the inner product of ax x minus ay times identity minus ax minus identity minus ay. So these are 4 descriptions of the same thing. So this probably here is simpler to grasp than that guy here. Okay, let's prove the equivalence. So first, that these two things, 1 and 2, are equivalent. That's immediate from the definition because the definition is symmetric in A and I minus A. So if we just replace A by I minus A, it's just the same. These two things just swap their places. And now 2 and 3. That's a bit weird. We use a pretty weird equality. It's totally elementary, but anyway. So the equality is if we take 2u minus v for some vectors in the Euclidean norm or in the Hilbert space norm, then this is the same as 2 times u minus v squared plus 2 times u squared minus v squared. That's not difficult to see. Just expand everything and it's fine. I find it weird, but that's how it is. So we use this with u is x minus y and v is ax minus ay. And then we get, so here we have this 2 times x minus y, and here we have 1 time ax minus ay. Okay, if we revise it, we end up 2a minus identity times x minus 2a minus identity times y squared, and again I have lots of previous 2 norms down there. Okay, this is now equal to, and remember that what u and v are is equal to 2 times I minus, no, it's a minus I, but it actually doesn't matter. A minus I x minus a minus I y squared plus 2 times ax minus ay minus x minus y, all is squared. And there's no 2 here. So from this, maybe did I screw something up? So I've now written that this says, no, that's 2. So now let's see. So this, let's assume 3. If this guy here is non-expansive, then this is smaller than the norm difference squared of x minus y. But then this here is actually 2 times the inequality over up here. So this shows that if this here 2a minus I is non-expansive, then a or I minus a is firmly non-expansive. And the other way around, if this here is I minus a is firmly non-expansive, then taken with this, you see that this guy here is smaller than the norm difference of x and y squared, which is also non-expansiveness. So that's already, from this here you can get this equality of 2 and 3. So let's do 2 and 4. So coming here, for this we just use that we may expand this identity minus a x1 minus identity minus a x2 squared, and if we expand it we end up with x1 minus x2 squared minus 2 times x1 minus x2 ax1 minus ax2, and then again plus ax1 minus ax2 ax2 squared. And if you plug that in here and expand everything, you see that this guy here is going to cancel. This is not going to cancel, and then they add up, and this goes to the right hand side, and that's it. Okay. 4 and 5 equivalent. That's actually clear if you just make your mind up what this here is, right? If you see what this is, you see that this is exactly this inequality here. There's just basically nothing to prove. Okay. Okay, and then we're almost done with the lecture for today. There were just 2 things which are left to do. So this non-expansiveness notion, that will be very important when it comes to algorithms once again. So in the next lecture we start analyzing algorithms, and we want to see that if we iterate just non-expansive operators, anything can happen. So we don't get a contraction, so we don't get a convergence. But if we iterate firmly non-expansive operators, things get a little bit better. And we're going to talk about this in the next lecture. But before we do that, let's first prove the important thing here about resolvents, namely that resolvents of maximally monotone operators are in fact firmly non-expansive. And after that, there's one more small result, and then we're done for today. 7th page already. So okay, the result is the proposition is called 2410, and so if JA is firmly non-expansive if A is maximally monotone. Okay. So maximum monotone operators have firmly non-expansive resolvents. So what we need is, we write down 2 things in the image of the resolvent, and actually we can write equal to. So yi is actually the resolvent of A applied to xi for 2 i's, 1 and 2. And this is the same as saying, again, we did that before, this is identity plus a to the minus 1. Rearranging gives us x1 minus y1 is in a of y1, and x2 minus y2 is in a of y2. So now we use monotonicity. We have two things in two different images, so we can say that the difference of the images, x1 minus y1 minus x2 minus y2, times the pre-images, these are now the y1 minus y2, this is non-negative. Looking what happens here, this is actually x1 minus x2 times y1 minus y2, and then minus norm y1 minus y2 squared. Okay. But now we know that y1 is actually the resolvent, and then we can conclude, so this goes to the other side, that ja of x1 minus ja of x2 squared is smaller than the inner product ja x1 minus ja x2 x1 minus x2. And actually we are done, so I've written too much in the lecture notes. Actually we are done because this is characterization number 4. So this implies 4 of proposition 24(9), and that's already it. So I think here I did the calculation once again, but that's really not necessary. I should shorten that. Okay, so that's then pretty much straightforward. And I just noticed that I think, yeah, so maximum monotone we need for domain, yeah, B for single values. Okay. So and the last thing is it's just a helpful lemma, which will be helpful at a later stage. So from now one probably not sees why this is important, but it's also an exercise in how to work with multi-valued operators. If A is maximally monotone, then you have that if you have the resolvent, which is single valued, and then apply A to it, which is not single valued, what you get is actually a single valued operator. So that looks a little bit weird, but especially it holds that AJA is single valued. Okay. Okay, so how does one go and prove such things here? So you want to know if this guy here is single valued. So we start with U being in AJA. I want to prove that A is of Y. Sorry, I want to prove that U is actually Y minus JA of Y. So what we do is we add J A of y on both sides, so u plus ja of y is then in a ja of y plus ja of y. So we just added one element on both sides, and here we can now factor, so we don't need linearity or something, we just factor out its identity plus a applied to ja of y, right? This is just how you apply sums of functions. So we did not use linearity of a because it's not true. Remember, this here does not use any linearity. It's just this is how you apply sums of functions, even if they're multi-valued. So identity applied to this is that, and a applied to that is this. But now remember that this here it's the inverse of I plus a. So they two cancel out. So this is multi-valued, this is not, but they cancel out. They just cancel out. So which means that this right hand side here is single valued, and actually this guy here is y. And that's it, right? If you now look at this, what we have here is u plus resolvent of a applied to y is equal to y, is equal to u is equal to y minus ja of y, which is identity minus ja applied to y. And then that's it. So this is how you can do such rearrangement of the inclusion with multivariate operators. Okay, so we covered quite some ground today. Let's recap maybe for a second. We started with the definition, not with the definition, but with the fact that for every monotone operator you can find at least one maximal monotone extension. In general, there are more, right? Remember that if we have here our coordinate system and our multi-valued operator may look like this, and this is what we have, then the maximal monotone extension we can to add this connection here, but here we could do like this or like that or like that or like that. They will all work. So it's not unique, this maximal monotone extension in general. It can be, but it's not. So we convinced ourselves that an operator which is continuous and monotone is also maximally monotone. And then we introduced the notion of resolvent. And convinced ourselves that resolvents are at most single valued if the operator is monotone. So the notion of non-expansiveness, I think, is very simple. And then we talked about the Minty parameterization, that monotone operators and non-expansive operators are in one-to-one correspondence by turning the graph by 45 degrees. It sounds so elementary, it is, so it's nothing difficult behind that. And the proof is also not hard. It's just this fiddling around with inner product and norm squared, but it has nice consequences. And the nice consequence comes from the fact that for Lipschitz continuous operators, you have always a Lipschitz continuous extension to the full space. If your Lipschitz continuous operator is not defined on the full space, you can extend it to the full space. And this allowed us to prove Minty's theorem, which says if an operator is maximal monotone, then identity plus positive number times a is onto. Yep. And this behind that is this Lipschitz continuous extension. So we also had a look at this graphical interpretation of what the resolvent is doing, but I don't find it that much enlightening. Why this? So of course, with this help, kind of can produce resolvents for maximum monotone operators, which you see, but you can also do it graphically, just scale them down by lambda, add the identity, and then flip the graph. So it's the same thing basically. Okay, and then we introduce the notion of firm non-expansiveness, which is a slight strengthening of non-expansiveness here by adding this norm squared to the left-hand side. We have numerous characterizations, so 4 other. This one is probably also interesting, that we can put this the other way. If you have a non-expansive operator and then identity minus 1/2 of that one, identity minus that one over 2, so this one is then firmly non-expansive. Did I get that right? Yes. Okay. But also these things are pretty simple to work with. Proof is again not hard, and then the last thing we did was to note that actually resolvents are firmly non-expansive. And then this is just an auxiliary result. We're going to need that later on, I guess. I think so. Okay, so that's it for today. 20 minutes early, but no one would complain, I guess. And so see you for the next lecture on Tuesday.